AMCASH, Advanced Materials Characterization Simulation.
As part of the AMCASH demonstration series, this presentation looks at the mechanical testing facilities at the School of Metallurgy and Materials at the University of Birmingham. My name is Richard Turner. So mechanical testing measures the material's mechanical properties, and this is particularly important for structural materials. The components must withstand specific stress-strain relationships under their in-service conditions, such as elevated temperature. Understanding the material properties allows for safe operation of the material. And this is even better if we can predict component life based upon the material properties. If we know the mechanical behaviour of a material, we can sensibly choose a manufacturing route. Some common mechanical testing methods are shown on screen. A simple compression or a tension test under axial strain conditions allows us to understand yield strength and ultimate tensile strength. A hardness test measures a material's hardness. A torsion test considers stress in non-axial conditions. A bending test determines how a material bends and bows. A shear test and a cupping test look at deformation. A scratch or a wear test determines how a material surface breaks down under a sharp instrument. We can also physically simulate other test conditions. For example, we can replicate an impact from a striking object with a known force using our impact pendulum. Or, if a material is at surface at elevated temperature, for example above 50% of its melt point, then the creep rupture test is important, showing how a material behaves at these high temperatures for a relatively low but prolonged stress. Cyclic stresses of a known amplitude and frequency can be applied to give a fatigue test upon the material sample. In our first mechanical testing lab, there are 5 screw-driven universal testing machines which can do tension and compression testing. We have another 18 servo-hydraulic universal testing machines, 4 of which have vacuum capability, 2 of which have an environmental temperature chamber capable of going from -170 to 300 degrees Celsius. 1 machine has biaxial loading. These machines can be used for tensile testing, for low cycle fatigue, crack propagation behaviour, 3-point bending and 4-point bending tests. Creep and stress rupture are possible. A fracture toughness K value can be measured. And using external heating, we can heat samples to up to 800 degrees Celsius prior to testing. In our second mechanical testing lab, we have 5 high cycle fatigue machines. These are capable of oscillating at between 50 and 110 Hz frequency, and they can determine a material's fatigue threshold point. They can operate in a temperature range from room temperature to 650 degrees Celsius. For our universal testing machine with biaxial loading capability, the frame is shown in the top left picture. The top right image shows loading along both the horizontal and the vertical axes with the component in the centre. The component is gripped top and bottom and left and right. The bottom right image shows how the component failed. We can use digital image correlation techniques to view the test piece during deformation and to calculate the strain distribution occurring over the test piece. And then on the next slide, you can see some of the digital image correlation results, which show the strain concentration around the component, and in this case, around the central hole within the sample. From the colour map, we can see that the red spots indicate high strain and blue is regions of low strain. If you have any interest in using any of the mechanical testing equipment that we have got as part of the AMCASH project, then feel free to either contact myself or contact the AMCASH project team.